Hello there and welcome to Lower 6th Further Maths A-Level. This is the core part of the sample assessment material, and here's question 6. We're working on a series question, but this first part is a proof by induction question. And this is a textbook proof by induction question here. The sum of r squared is equal to 1 over 6 n plus 1, n and 2n plus 1. Right, so starting in the same point we always do with proof by induction, and that is to prove our theorem true for n equals 1. So it's the formula substituted in with a 1, so it's the sum from 1 up to 1, this is the left hand side we're working on here, of 1 up to 1 of r squared. That means you substitute in the numbers of 1 into that squared formula, so it's going to be 1 squared, which is just 1. And on the right hand side it's going to be substituting in 1 where we have an n in our formula here, so it's 1/6 of 1 times by 1 plus 1 times by 2 plus 1, and that will also give us 1. So here left hand side equals right hand side, and that's all groovy to get us started on the next step. The next part is we assume our theorem is true for n equals k. So therefore the series of 1 up to k of r squared is equal to 1 over 6 k, k plus 1, 2k plus 1. The next part is the key part is that we prove our theorem is true for effectively the next value up from k, and therefore if we can start at 1 and prove the next step up and keep that iteration going, then we can prove our theorem is true for all positive integers. So prove true for n equals k plus 1. So here is what we need to do then. We want to show that the theorem that sums our square numbers from 1 up to k plus 1 can be represented as 1/6 of, and then substituting k plus 1 into all of these n values here, k plus 1 times by 2 lots of k plus 1 plus 1, and this is what we want to show. So let's start working on the left hand side of this. We have the series of 1 up to k plus 1 of r squared. Let's think about what this is. This is just adding together a whole bunch of square numbers up until we reach k plus 1. So it's 1 squared, 2 squared, 3 squared, plus we go through k squared and we go through k plus 1 squared. Right, let's try and break this up into something that we know then. We know that the series of the square numbers from 1 up to k, so just these ones here up until k, can be represented with this formula. So that's what we'll do. We'll represent the first k terms with this formula here. And then we just need to add on the next step, which is the next square number from there. And generally you'll see that all series proof by inductions follow this roughly the same pattern, that you use your formula for your first k terms and then you add on your k plus 1th term. So what we're going to do now, I'm also going to squeeze in here a 6 over 6, because what I'm going to do with this term here up in this next part here is factorise it and try and turn it into what we've got here, or in fact what we've got in our want to show part there. So this expression down here is going to equal, factorising it, pulling out factors now. We've got a 6th in both of these terms here, and I can also spot here that we've got a k plus 1 here and a k plus 1 here. So in terms of factorising it, I've pulled out another factor. That's k plus 1, and I think that's it. Now what have I got left over such that when I expand my brackets I get this expression here? Well, I'm going to need a k and a 2k plus 1. And I'm also going to need to add in, well, I've taken out my 6th, I've still got my 6 that I need to factorise, and I've pulled out one of these k plus 1s, so I need another k plus 1 to go in there with the 6. So let's expand this bracket now, not the whole bracket, we obviously don't want to do that, otherwise it would have been pointless factorising, just inside the square brackets here. So we're going to get a 2k squared plus k plus another 6k later on, that's 7k, and plus the 6. And this will factorise down to 2k plus 3k plus 2. Right, we're nearly there. We're nearly at what we want to show. Now I can spot here the k plus 2, that's very similar to this k plus 1 plus 1. So that's how I'm going to phrase it such that it looks exactly like what I want to show. So I've got my k plus 1 plus 1 there. And the next part here, which is 2 lots of k plus 1 plus 1, is exactly what I have here when I've got a 2k plus 3. So that's all nice and lined up. And this is exactly what I have on the right hand side of my WTS. So I've gone through here, going step by step through the algebra, such that I've proved what we want to show from the left hand side to the right hand side by doing some maths. Right, step 4 is always an important step as well. It's the conclusion part. So what we need for the conclusion part is, as we have proven true for n equals 1, and we have assumed true for n equals k, we have proven our theorem true for n equals k plus 1. Therefore, by mathematical induction, our theorem, which is this thing up here, and you'd have to write that down, is always true for all positive integers n. Make sure you don't miss out that last bit. This theorem isn't going to work for all numbers n. If you substituted in 3/4, this theorem doesn't work. It's only positive integers n. So make sure you write that in right at the end. Okay, part B comes along, and now we're back onto the series part of this question here, using the standard results for the sum of r cubed and the sum of r. Show that for all positive integers n, this theorem here is true. So I'm going to ignore the right hand side for now and just concentrate on the instructions they've asked us to follow. The standard result for the sum of r cubed is this, and the sum of the r numbers is n over 2 n plus 1. Okay, so what we want to show then is that this theorem here, which is the sum from 1 up to n of this bit of algebra here, is equal to this. What I'll first do is expand this algebra inside here. So we get an r cubed minus 6r squared plus 6r squared, which cancel out. So it's just minus 36r. Okay, so what we have next is to split this up. So this is going to be the sum of r cubed take away 36 lots of the sum of r. And now we substitute in our formulas. We have a formula for this part here and a formula for this part here. So this is going to be equal to n squared over 4 n plus 1 squared, take away 36n over 2 times n plus 1. Now before we start factorising, I always like to make the denominators equal such that I can pull out those denominators with ease. I need an over 4 in the second part, so I need 32n to keep the expression equivalent. Now I'll start my factorising. I've got n in common in both terms, I've got n plus 1 in common with both terms, and I've got a divisor of 4 in common for both terms. And what I'll have left over is n from the n squared, n plus 1 from the n plus 1 squared, and that's what I have left in the left hand term. With the right hand term, all I've got left is the take away 72. I've got my 4 out, I've got my n out, I've got my n plus 1 out. That's all I've got left, unfortunately. Or fortunately, because this is the right answer. So, what should we do next? Well, let's expand what we have inside that square bracket, and it's n squared plus n minus 72. Okay, let's try and factorize that now. It's a quarter n plus 1. And the clue here is in the answer that they've given us. Does this equal what we have here? Yes, so might as well use it. N minus 8, n plus 9. You can see that when you times these together, you're going to get a minus 72. And when you add the expansions here, you're going to get an n. Perfect. So, part C is now to evaluate when these two expressions are equal to each other, find the possible value of n. So what we'll do is use the formula that we found in part B, which was a quarter n, n plus 1, n minus 8, n plus 9. So that was the formula for this part here. And the formula for the sum of r squared times by 17 is going to be 17n over 6, n plus 1, 2n plus 1. So given that n is a positive integer, we can cancel these out. Cancel out the n there and there. N plus 1s can go as well. Okay, let's times through by a value that will get rid of these fractions. So we'll times through by a 3 to get rid of that one there, and another 2 to get rid of that one there. Let's times through by, I think we need to times through by 12. So times by 12, and we're going to get 3 lots of n minus 8, n plus 9 is going to equal 34 lots of 2n plus 1. Okay, let's expand our brackets now, and we're going to get 3n squared plus 3n, it's going to be minus 72 times by 3, and that's going to be minus 72 times 3, that's going to be 210, add 6, minus 216. Which is going to equal 68n plus 34, and then we'll shift everything onto one side, and we'll get 3n squared minus 65n minus 250 equals 0. Can we divide through by 3? No, I don't think we can. We can factorize it to 3n plus 10, n minus 25. So therefore either n is equal to minus 10 over 3, or probably not because n has to be a positive integer, or n equals 25. So that there is the only positive value that we have for our n here, so that is the answer to part C, n equals 25. Okay, that was a really long question, well done if you followed that, 15 marks in total.